on YouTube because of FERPA. Got to be careful about that one. All right, well, it's some version of the internet is working apparently. Okay, nice to see everybody. There's still some students left. That's great. Right, so let's see here. In terms of announcements, all that good stuff, you have your skinning homework, I guess, will be due a week from yesterday. Is that right? Or was it due yesterday? Due tomorrow. What day is it?
Tuesday.
Oh, it's Tuesday. Is it Tuesday? All right, yeah, your homework's due tomorrow, so you really should get started with that. Yeah, absolutely. If you haven't already, then good luck with that. Really, I do think they get easier from here on. I think this is probably the trickiest of the homeworks in this course. Yeah, so other than that, your nano quiz should go out at the end of lecture. Zoe, could you double check that the nano quiz exists, by the way? Nobody responded. Oh, okay, cool. And other than that, I think it's just another normal week in paradise here in Boston. Actually, it's beautiful outside, so I see why you're not, here. Right, so any questions, concerns, comments? Like fun animal videos to share?
When should we expect to get the grades to put that one back?
Soon, yeah. We're working on that. Any other questions? Excellent. All right, folks. Well, in that case, we are going to continue today in our discussion of rendering, everybody's favorite topic in 6837. And essentially, what we're going to do is add to our repertoire of shapes that we know how to draw on the screen, right? So our plan for today, we're going to spend the first part of our lecture today talking about triangles, everybody's favorite shape, certainly my favorite shape. And after that, we'll talk about how to get some interesting geometry in a ray tracer using a technique called constructive solid geometry, or CSG. And we'll see that it's a really interesting strategy for rendering an object even though we don't actually have its geometry on hand, which is kind of a neat trick that we can do in ray tracing that would be very difficult to do in other types of rendering. So it'll be kind of a fun idea to explore toward the end of our lecture today. And then after this, we're going to start diving into all kinds of different specialized topics in rendering. So we'll talk about how to make ray tracers not painfully slow. We'll talk about different lighting effects and materials, all that good stuff. Okay, so as a bit of a recap from our previous lecture, I think all of us probably know what the term rendering means, but in case you forgot, it's essentially the procedure of preparing an image for the computer screen given the description of a scene that you're trying to draw. And essentially, there's sort of two big variants of rendering algorithms out there, right? There's ray casting / tracing, depending on whether it's recursive or not. And then there's rasterization, right? So, and this has to do with like, in ray tracing, you produce a bunch of rays, and then you figure out which one each object runs, each ray. Let me try that sentence again. You produce a bunch of rays, and you figure out what object those rays run into. And then in rasterization, you iterate over each object and you like paint it one at a time, right? That's the basic difference. So in our previous lecture, we went through the really basic kind of aspects of ray casting, right? Like how to produce the rays coming from your eye into this little virtual screen in front of you, including two different cameras. And remember, an important detail is that we represent a ray as basically an origin point plus some parameter t times the direction. And then our task for rendering was to figure out the first non-negative t that runs into an object in our scene. And we did that calculation for two ridiculously boring shapes, a plane and a sphere. And now we can basically draw a bunch of round stuff sitting on flat stuff. Any questions about our story so far? Cool. All right, so today we're going to do the important calculation for your ray tracer, and it's the one that, I think one thing that you've probably seen is in a lot of graphics, like we work through computing some formula and then we just have to type it in really carefully. And this is another one of those. In particular, we're going to work through how to intersect a ray with a triangle. Right? And the second that we can do that, we can render a huge chunk of the 3D geometry that we have out there in the universe, because as you already know, we tend to store shapes as triangle meshes. And so essentially, that's going to be our main task for today, is to figure out how to do that. And as a reminder, we're about 82% of the way there in some sense, right? Because in our previous lecture, we already talked about how to intersect a ray with a plane. And that's like kind of, somehow it feels like you're almost almost there to intersecting a ray with a triangle, right? Because once you know where the ray hits the plane, the question is just, did it go through the triangle or not, right? Because if it did go through the triangle, then you can render it like a plane. If it didn't go through the triangle, you shouldn't render that triangle at all, right? And so that's the kind of high-level picture. But what we're going to see is that an alternative version of the ray-plane intersection calculation is going to lead to a convenient coordinate system for this kind of math. And it's one that's going to come up a lot in graphics. So this is the thing that's really worth understanding because it's one of these terms that just we see everywhere. And that is the idea of barycentric coordinates. Okay, so essentially, the way that we defined a plane in our previous lecture, if you recall, was with, so there it is. That is the universal mathematician diagram for a plane. And last time, we defined a plane using like a point and a normal vector, like that. And of course, that's a completely reasonable way to describe a plane, right? And if I had, 3 points in my planar object, I could very easily find a normal vector and get this representation. But a different question you might ask is, well, maybe I have 3 points like A, B, and C or whatever. Can I work with those points directly and do ray plane intersection working with like maybe a triplet of points rather than a point and a normal? And that's going to lead us to this idea of barycentric coordinates. In particular, let's say that I have 3 points. I'm going to label them for consistency with today's lecture. I'm going to make my points like A, B, and C. What defines a plane in terms of A, B, and C? Like, how could I go about defining a plane here? There are many different options. I see a hand. I was getting nervous. You were late, and I thought, like, nobody's going to answer my questions. Yeah.
Well, we could like have two vectors that span the planes. For example, B minus A, C minus A.
Sure. I could have, let's see, B minus A, C minus A, like that, right? So then a point in the plane would be A plus some parameter times this vector plus some other parameter times that vector. Sure, that's a perfectly reasonable parametric definition of a plane. Any others? There are many. Yeah. Yeah, so one thing I could do is just recover the representation that we had in our last lecture, right? So I could take the cross product of these 2 vectors, get that normal, and now I'm back to last time. There's actually a third one we're going to work with today, which is that the plane through this triangle ABC can also be defined as the set of all weighted averages of A, B, and C. Right? So if I take 3 numbers that sum up to 1, so for example, alpha, beta, and gamma, and I have the property that alpha plus beta plus gamma equals 1, then I claim that the following point is in the plane, namely, I don't know, P of alpha. You guys might have noticed I have a bad habit of writing math and then looking at my slide and realizing that the math doesn't quite agree with the letters that I chose in the slides. In any event, if I have alpha times A plus beta times B plus gamma times C, this is like kind of like a weighted average of alpha, beta, and gamma. Do you see that? Because the weights are like things that sum up to 1. I claim that this point always lies in the plane between A, B, and C.
Alpha, beta, gamma can be negative, right?
They can be negative, yeah. And we're going to talk a little bit about what that means. But for now, any 3 numbers that sum up to 1, if I added these all together, I'm going to get a point in that plane. Right? There are many different ways to see why that's the case. So for example, maybe I kind of add and subtract. So like I could try and write it in this representation easily enough. And we'll do that in just a moment. OK, so that actually leads to this sort of barycentric definition of the plane, which is that if I have a non-degenerate triangle, obviously if A, B, and C are all along a line, this is like not a great definition, then I can get any point on the plane as alpha times A plus beta times B plus gamma times C. Now, maybe you don't believe me, so let's make sure that that's actually the case. Notice that, let's say that I have, I'm staring at my slides to make sure I use the same notation. Yeah, let's say that I know beta and gamma. Do I really need alpha? That's right. So alpha is really just 1 minus beta minus gamma. If I have this assumption, they sum up to 1. Right? So let's plug that in. So I have 1 minus beta minus gamma times A plus beta times b plus gamma times c, like that. And in general, like whenever you're at a loss for what to do mathematically, you might as well kind of regroup and just kind of see what happens. So in particular, let's factor out the beta and the gamma and see what's left. Okay, so what am I going to get? So for 1, I have this 1 times a, so that's just by himself or herself. I have beta, and notice there's a minus a times beta here and a plus b. So this is plus beta times b minus a plus gamma times, let's see, there's another minus a and a plus c. C minus a, like that. Everybody agree with me? We should all think, because remember that I am horrible at arithmetic. Okay, so conveniently, let's take a look at our diagram on the left-hand side. Well, look at this vector b minus a. That is exactly this vector here, right? And similarly, this guy, c minus a, well, that's the vector from a to c, right? So notice what I did. Well, my point P here is a point A, right? That's like a point in my plane here, plus some beta times the vector B minus A, plus some gamma times the vector C minus A. You see how we just converted from our barycentric formula actually to the previous one that was kind of suggested earlier in lecture? So hopefully that convinces you that essentially this thing is a point in our plane, yeah? And if you think about it a little bit, it has to be the entire plane, right? Because there's sort of 2 degrees of freedom here, right? There's 3 numbers and a condition that they sum up to 1. So the 3 minus 1 is 2. And so we get the entire plane that way. Does this story make some sense? So the alpha, beta, and gamma are going to be called the barycentric coordinates of our point. And we're gonna see what that means, because it's going to have all kinds of really nice interpretations that we're going to make use of in graphics class. And in fact, we're going to just keep reusing it. So like today, we're going to use it for intersecting rays into triangles. We'll see that it's also useful for shading and texturing and a lot of other stuff too. So this is just the beginning, and this is one of these ideas that just recurs over and over again. Incidentally, if you're looking for a fun Googleable advanced topic term out there, you can search for the phrase generalized barycentric coordinates, which would be like I have more than 3 points, and I want to express something inside of a shape as a weighted average of more than 3 points. So now there's like some engineering decisions I can make in terms of what weighted average I want. And so like tools like Photoshop often use this, where like I'll draw a cage around a shape and start deforming the cage, and I want the shape to deform with it. So anyway, that's just a fun thing to look up later. So quick question. So here we have a function from alpha, beta, gamma to our point P. If you remember our terminology from our previous lecture, would we call this an implicit or an explicit definition of a plane? Kind of one, kind of the other. Well, I argue this is pretty explicit, right? Like I'm giving you a map from alpha, beta, gamma into the plane, right? So it's sort of like explicitly giving you points, right? Remember that like an implicit thing would be like the set of all points that satisfy this relationship f equals 0 or something like that.
Kind of because of the constraint.
Yeah, I guess that's true. Yeah, I don't know. I'm not going to make an exam question out of it. So, yeah. Right. And if you're curious, this word barycenter is a loaded term. Actually, kind of literally. So in particular, like if I put weights on A, B, and C, which were kind of proportional to alpha, beta, and gamma, then the point that the triangle would kind of balance on would be exactly the one that's parametrized by those 3 numbers. Fun fact. One of many interpretations we'll have of barycentric coordinates today. Okay, so in particular, so one thing that already we've asked about, if we look at these 3 values, this is a definition of the entire plane, right? Like alpha and beta could go negative. What is special if all 3 of alpha, beta, and gamma are positive? Like what do you think that corresponds to? I see your hand there, but we're going to try at least one other person today. I know at least one other person in this room has like a lucky guess that they're almost certainly correct. When all 3 barycentric coordinates are positive, I'm taking a weighted average of these 3 points. I see you nod. No, you're not going to speak. It means we're in the inside of the triangle, right? Because we're like taking a weighted average of A, B, and C with positive weights, right? So you're kind of like in the interior. Yeah.
I always thought you would always come inside the triangle because I assumed that like kind of B minus A and then C minus A kind of acted like as like barriers. That's kind of how I interpreted. But I think that I didn't take into account beta and gamma.
Yeah, so like let's say that beta is -1 and gamma is 0, right? Then what would that correspond to? That would be like, so it's beta times B minus A. So I would start at A. I'd take this vector, multiply it by -1, so I'd end up somewhere back here. Yeah.
Okay.
Excellent question. Any others? Right, so the high-level point, the one that's really important to remember is when your barycentric coordinates are positive, or at least non-negative, then you're inside of the triangle. And that's going to be super important because at the end of the day, our goal is to render a triangle, right? So how do you think we're going to do that? Well, we're going to try and find the barycentric coordinates of where a ray runs into that triangle. And then essentially in your code, you're just going to check if those three numbers are positive. And if they are, then you're in good shape. Yeah? Right, so that's our basic scenario so far. Any questions about our high-level goal for the day? Now we're going to have to do a calculation, which is kind of similar to the ones that we've done in the last lecture, just with barycentric stuff. Yes?
I guess we don't maybe need to be like that in our code, but checking if things are positive in double precision or something like that, we may encounter like problems, no?
Yeah, that's a good point. So in general, you have to be quite careful when you deal with floating point precision. This is absolutely right. So oftentimes, we're going to talk a little bit about this later in lecture. We have to build in a bit of a fudge factor in terms of like, well, when things are positive, maybe you want to put like a bit of a margin on one side or the other. I think specifically for barycentric coordinates, it's not a huge deal, but there are other places in the rendering pipeline where this becomes a big problem. In fact, the very first time I taught graphics, which was roughly, oh God, more than a decade ago, is that right? I was a grad student, so I was like optimistic about the scale of the homework I could assign to these folks over the summer at Stanford, and I gave them a rasterization assignment where all you have to do was rasterize two triangles, and that shared an edge, and the deal was that if you ever light up 2 pixels for the same let me try that again, 1 pixel for 2 different triangles, then you lose credit, and it turns out to be ridiculously hard to get that right. So like all I want to do is draw 2 triangles that share an edge and have them be seamless. And it turns out because of rounding stuff, it's just really easy to accidentally like leave a hole somewhere in between or like have 2 things overlap. And so if you really want to do it correct, you have to like read through like IEEE floating point precision, like this thing rounds down and that thing rounds up and these are consistent and all that kind of stuff. It's no fun at all. That has since been removed. Okay, so right, so there's our basic summary so far. We'll point inside of the plane so long as alpha, beta, and gamma sum up to 1. Notice if they don't sum up to 1, this is just like a point in 3D, right? Because it's like a linear combination of 3 things. Moreover, if all 3 of them are positive, then we're inside the triangle. So now our task is just to find these numbers, and then we're in good shape. Incidentally, there's sort of a classical way to compute barycentric coordinates, and then there's the one that we actually do. If you took high school geometry class, you probably have heard of the barycenter of a triangle. That would be the, I see the eyebrow. Yeah, if you recall, that's 1/3, 1/3, 1/3, just like the average of the 3 points here. It's typically the term that you would remember from there's like in-center, barycenter, circumcenter, and a few others. I always got these things wrong in high school. But actually that leads to kind of an interesting picture for how to interpret alpha, beta, and gamma. So here's how we can do it. So let's see if I can get this right. So here's our triangle. Somehow the bigger you draw geometry diagrams, the easier they are to think about. So if I have C, A, and B, this only works if you're in the inside. So I have some point in the interior, and I want to know its barycentric coordinates. One way that you can do it, which is kind of fun for me, is if you take the triangle, you can divide it in 3 by drawing straight lines from that vertex to all 3 of the vertices of the triangle. And you can look at the sub-areas of the 3 triangles, okay? So usually, this is where the notation gets a little bit confusing. If you have a vertex C then you would call the subtriangle corresponding to C as the only one that doesn't touch C. It's opposite, okay? So let's say that this thing has area A sub C. This one has area A sub little a. This one has area A sub B. Does everybody kind of understand the picture here? So if we call the area of the entire triangle the sum of these things, then I can get the barycentric coordinates by looking at ratios. So like for instance, alpha, which is the barycentric coordinate of A, is going to be the A over the ratio, or over the total area. Beta is AB over the area, and gamma is AC over the area of the triangle. And this is one of those formulas you should look at and then kind of sanity check with the diagram and kind of make sure that this makes sense to you. So for example, what would be the barycentric coordinates of just like the vertex A? Well, in like, if there were order in the universe, you'd hope it would be 1, 0, 0, right? So let's see if that's right. So let's say I'm at the vertex A. It's like I'm over here. What is the area like A sub B and A sub C? 0. Thank you. What's the area A sub A? Everything else. Right? So if you look here, right, so A sub A over the area of the triangle is 1, and these two numbers are 0. Right, so that's why this diagram kind of makes sense, right? Like as I move closer to A, the area opposite A gets bigger. That's the way to think about it. And there's actually a lot of things you can do. So for example, if I'm on like the segment between A and B, right, then we know that A sub C is 0. So there's actually a lot of geometric information that you can get out of this picture. Does that make sense? So we're not going to prove this formula in class. It's kind of like just a fun fact, but it's nice to know this is the classical way to get this. In fact, probably what you learned in high school geometry was that the barycenter of the triangle is the point that makes these three areas the same. Or, I don't know, I think there are a lot of, Euclid has all kinds of clever ways to write down that condition. Okay, now we're all grown-ups here, so rather than doing these cute geometry diagrams, we want to just do like algebra and like numbers and stuff. And so that's what we're going to do today, is the sort of just linear algebra approach, which is like the far less elegant sledgehammer way to compute barycentric coordinates. So in particular, in some sense, I don't really need alpha, beta, and gamma. It's enough to just have beta and gamma, and then alpha has just got to be 1 minus the other two guys. So we're going to start there. So in particular, is it okay if I erase this triangle here? We're good? Yeah, I think this diagram makes some sense. Okay. So here's our triangle again. C, A, B. Like that, and I've got some point P. And P is in the interior here. So I'm going to define two different vectors, this guy and this guy, which are ones that we've already kind of talked about today. And we're going to call these E1 and E2. E stands for edge, yeah? Okay, so mathematically, what is E1? I know you guys know how to do this. One more time? B minus A. There we go. Okay, and E2, C minus A. Awesome. Okay, so what is our point? Well, we can write it as follows. I can say that P is equal to A plus beta E1 plus gamma E2, like that. Cool? All right, so that's going to be our basic setup here. Now, let's say that I had, like you gave me a point, and then moreover, you told me it was inside of the triangle somewhere, and I just wanted to compute its barycentric coordinates. Notice that I could kind of do that from this condition, right? Like, so there are actually 3 coordinates, like px, py, pz, and there's 2 unknown values, right? Because I know p, and I'm just trying to find its coordinates inside the triangle, right? So there's beta and gamma. Notice that there's something is a little bit wrong here. Like there's a linear system of equation, and we actually have 3 rows. This is secretly 3 different equations, one for x, one for y, and one for z. And there's 2 unknowns, yeah? The reason for that really is that like somehow this expression doesn't know that the triangle makes a plane. but if you already told me a priori that P is inside of the triangle, so we're not going to worry about that fact. Then one thing we need to do is just reduce this thing down to like a 2x2 system. Right? So one reasonable way to do that is to take the dot product of this expression and E1 and E2. So in particular, I could do the following. I could say that 0 is equal to E1 dot product A plus beta E1 plus gamma E2. And 0 is equal to E2 dot product A plus. Notice you can't follow all of these arrows backward, but you can follow them forward. That's fine. Okay? So our basic setup here is you gave me P, and I'm trying to find the barycentric coordinates of P, assuming that I'm inside of the triangle somewhere. That make sense? Oh, I just subtracted P from both sides.
Oh,
Yeah. Oh, but I forgot to write P. I should look before I answer your questions. There you go, like that. Good catch, thank you. All right, any other mistakes? They're highly likely. Okay, so this is all fine and good, but it's kind of ugly. So let's write this. So here's our expression so far. One nice thing we can do is just write this as like a 2x2 matrix system, right? So in particular, let's say that I have my unknowns, beta and gamma, like that. Then I want to write some expression that looks something like this, right? Okay, so what is the coefficient in front of beta in our first expression? Well, it's E1 dot E1, right? Like that. The coefficient in front of gamma is E1 dot E2. Similarly, down here, like that. You tell me, which one is it? It's both, right? Dot products are commutative. Okay, and what's on the right-hand side? What's kind of all the stuff we didn't account for, right? So here, I guess it would be E1 dot A minus P. The sign changed because I moved it back to the other side. And this is E2 dot, oh, P minus A. Thank you. P minus A, and that's a P minus A. Have I managed to confuse you all yet? Because I can keep trying to make more mistakes. It's good. I'm testing if you're paying attention. Yeah. Okay, so at the end of the day, even if you can't read my horrible handwriting, the good news is that it's on the slide. So we get exactly this 2x2 system of equations. And I can invert that matrix on the left-hand side, and what I get is a formula for beta and gamma in terms of basically stuff I can compute from the triangle on my point P. That make sense? All right, so the problem we've solved so far as our kind of warm-up problem is given a point in our triangle, we can indeed compute its barycentric coordinates. But of course, that's not exactly the problem we really wanted to solve, right? What we really wanted to solve was something that looks kind of like this diagram, right? So we're given an array. Remember that array is defined by an origin and a direction. We're given the 3 vertices of our triangle, and we want to find the point P and its barycentric coordinates of that intersection between those two things. That make sense? Notice that this problem is going to, I would classify this problem as mildly annoying because there's like a lot of variables flying around, right? We need to compute alpha, beta, gamma, the t, and we have to work with like A, B, and C, and the origin and the direction. There's a lot of kind of things flying around. And that's just kind of life in the city. This is just an annoying calculation, but it is one that we have to do. So that's too bad. So what would be a good strategy here? Essentially, we have sort of an explicit formula for our plane, right? Like all the points on our plane are these weighted averages of A, B, and C. And we have an explicit formula for our array, right? Like the origin plus t times the direction. What should I do? Let's think for a second. Think to our last lecture. Like how do we do this? So the array is defined by like a t. The plane is defined by alpha, beta, gamma. So maybe, yeah. Yeah, so like maybe I set these two things equal to one another and we see what we get. I'm sorry, I'm looking right past our colleague in front of me because I know he knows the answer, and we gotta be a little more democratic today. All right, so in particular, we sort of have two different formulas for our point P, right? We've got like a P of T, which is the point on the ray, and we've got like a P of maybe beta gamma. We decided we didn't really need alpha. And then what we want to do is set those two things equal to each other, and that's the point of intersection. Does that make sense? So you can kind of think of this like target practice, right? Like you've got this T, which you're like sliding along your ray. You've got this beta and gamma, which is like sliding along the plane, and you're trying to kind of make those two meet up with each other. That's the way I like to think about this problem. All right, so the question is, do I want to write all of this down? The answer is no, because I'm lazy. So here we are gonna work from the slides, but I know that slide math is a bad habit for professors, so I'm gonna be purposefully slow, and we're gonna take lots of deep breaths. Okay, so in particular, if we look at our second line here, what did I do? Well, I just on the left-hand side, I plugged in the formula for my ray, right? The origin plus t times the direction. And on the right-hand side, I plugged in my formula for the plane. Does that make sense? Remember that my unknown here are t, beta, and gamma. Any questions so far? Excellent. So essentially, that's it, right? So think about, so what are my unknowns? They're t, beta, and gamma. So I can just reorganize that expression and kind of write it coordinate-wise, right? Because there are three unknowns, and there are three coordinates, right? There's x, y, and z. So in particular, I really have these three expressions that I've shown you on the top of the slide. You can see why I didn't really want to write it down. Does everybody understand these three formulas? I don't think you need to write them down. I think it's basically just taking the last slide and putting like subscripts next to all the letters, right? So essentially all this is saying is that at that point of intersection, the left-hand side is the point along the ray, right? The origin plus t times the direction. And the right-hand side is the point on the plane, and that those two things should meet up. Yes?
Wait, what is t here?
T is a great question. T is the parameter along the ray. So remember that the ray is defined by a head chalk.
Like RO plus TRD.
That's exactly right, right? So T is.
RO and you give RD.
Mm-hmm.
And then how do we get T?
That's a great question. So we're actually given a lot of information. We're given RO, we're given RD. That's what's defining the ray, right? And so that comes from like the eye and the camera and all that stuff. We're given A, B, and C because that's defining the triangle. The things that we don't know are T, alpha, beta, and gamma, right? We eliminated alpha, and now we're left with T, beta, and gamma. And so I haven't told you how to compute them, but hopefully you agree with me that these three relationships are true, right? This is saying that the ray meets up with the plane. So all I'm going to do is take these things and just rearrange them into the expression on the bottom here. Notice that this is just like a fancy matrix way of writing what's on the top. And so what do I have? I have a 3 by 3 matrix on the left-hand side. I've got three unknowns. What am I going to do? Yeah, just invert the matrix, right? So in one shot, I'm going to get beta, gamma, and t. Yeah. Does that make sense to everybody, how we're going to get all those three unknowns? Here's the good news. This is like not the kind of thing that you need to like memorize. It's the kind of formula that you write down on your scrap paper and you work out and you type it in very carefully. And then you're going to get a sign wrong and like your ray is going to intersect in a weird place, and then you'll spend a lot of time looking for that one minus that should be a plus. That's life. Okay? There are many ways to invert 3 by 3 matrices. You guys have taken linear algebra more recently than I have, so you probably could name like a long list of those. One of the common ones that I always found to be particularly obtuse, but is a good formula for 3 by 3 matrices, is to use this Cramer's rule thing. You guys, did you encounter that in your linear algebra course? This thing with minors of matrices? It doesn't really matter. This is just some way to invert a 3 by 3 matrix. Incidentally, probably nobody would bother in graphics. Probably what we would do is just write down this system and then call a piece of code for solving the 3 by 3. I don't think anybody would type in the formula for an inverse of a matrix anymore. In fact, there's good reason not to, right? Because there's a division here, and it turns out that there's some odds it's numerically unstable, so it's like better to like trust somebody else's numerical code than write your own. And that's it. Do you see? Now our problem is done. In fact, it's enough to just like if I wanted that intersection point, now that I have t, how could I get it? Like if I actually wanted that point in 3D where the plane runs into the ray. Yes?
We can use we parameterize our points by t, so we can just plug in t.
Yeah, remember O plus T times D is that point on the plane. Can somebody give me a second way I could get it from the values on the screen? Yeah. Yeah, that's right. Like I also have the barycentric coordinates, right? So I could also get it by using the triangle. And those things will meet up because that's exactly how I computed these things. Isn't that cool? I think this is kind of fun. Okay. How do we get alpha, by the way? Yeah, it's 1 minus the other 2. Okay. As always, anytime you see division, you should get suspicious. There is a chance we divide by 0, and what would that correspond to? Like what would that mean in your code? I'm expecting like some hand gestures here. Like where's our ray and where's the plane of our triangle? There you go. They're like going parallel to each other, right? Because then they just don't intersect. Any questions about that little derivation? This is one of many formulas in graphics that is like big and annoying, and you just have to type it in and like put it in a piece of code that you never look at again until it goes wrong, and then like you spend like weeks debugging because you don't think to look there. Not that I have a lot of experience with that. Okay, so barycentric coordinates are super, super useful for like a million billion different things. So far we've used them just to run rays into triangles. Notice that our ray tracer just got a lot more powerful. Right now we can render bunnies, and that's really what we want in graphics. But it turns out there's a lot more we can do with that. In particular, one of the earliest ideas in kind of graphics history is this idea of barycentric interpolation. And you've actually already interacted with this a little bit on your problem set. So let's say that I want to render a triangle, and I want to color it in some smooth way. So like I have a color on each of the 3 vertices, and I want colors in the interior of the triangle that aren't just flat, right? Like not just a constant. But one thing I can do, remember that in essence, like the right way to think about barycentric coordinates is that they're giving me weighted averages. So like let's say that I have the red, green, and blue vertices here. I want to know like the color of some point in the interior. What would be like a reasonable way to do that, to get some smooth interpolation? Anybody have any ideas? Yeah. Cool. We're going to return to your question in just a second. How do we get that color? Yeah. That's right. Like just reuse the weighted average that you got to get that point, but now take like a weighted average of the colors. Yeah. What's your question? If you have I didn't quite understand your gesture there. Here's our triangle. Yeah. So you do, so triangles aren't really two-sided, right? It's just a plane, so I'm not sure if it matters what side it's coming into, but maybe I'm misunderstanding it.
In the triangle, there's a
Oh yeah, there are these annoying boundary cases where you're like dividing by 0. So essentially like the ray is parallel to the triangle, right? In that case, you just have to come up with a policy for what to do, right? I mean, the triangle is infinitesimally thin, so there's really nothing to draw in that case. This is probably a case where that fudge factor we were asking about before would start to matter. Of course, the probability of that happening is 0, but sadly for us, those low probability events often happen because in graphics, we like to draw things from interesting camera angles that tend to be the ones that are like really annoying to deal with. Yeah, it's a good question. All these boundary cases are good things to like try and drum up in your head because they come up, and you don't want to cause frustration when somebody's working with a graphics tool and suddenly it explodes because they like put the camera somewhere you didn't anticipate, right? That wouldn't be so good. So, right, so this is this idea of barycentric interpolation, right? Like if I have 3 numbers that are essentially decorating the vertices of a triangle, then I can interpolate those numbers, whether they're colors or anything else, to the interior, and that's a perfectly reasonable thing. Can anybody think of other stuff I might apply barycentric interpolation to? So remember you wrote in your assignment, you wrote code for loading meshes, that was decorated with some information. Yeah. Yeah, normal is a fabulous idea, right? So remember that like your triangle meshes had like a normal vector per vertex, which if you think about it doesn't really make any sense because like triangles are flat, so like why do you need a normal vector on the vertices? So like a pretty typical shading model. will take the normals per vertex, and then when you render the triangle, rather than rendering it as like a little piece of the plane, they'll actually use barycentric interpolation to kind of interpolate those per vertex normals to the interior, and then use that for shading, right? And the reasons that's kind of simulating a smooth surface. Otherwise, when you render your surfaces, they'll all look like they have a bunch of facets, right? Which might not be so good. Yeah.
Oh, I have a question.
Awesome.
So, when you're like doing barycentric coordinates, like for example, like this is one triangle and it has a nice gradient. If you have like a teapot and you want to move gradient across the entire teapot, like,
Mhm.
would you have to like manually assign each triangle mesh like a very specific coordinate, or would you write an algorithm that does it?
I think you probably write some code to do that for you. Yeah, if you want something that's smooth across an entire domain, then yeah, I mean, currently we're talking about things that are defined per vertex, but sort of the role of the artist or the algorithm would be to fill in that sort of larger scale picture. There are many ways to do that. If you've encountered the Poisson equation in your math classes, that's one kind of typical one, which would say like I want the gradient of my function to be as smooth as possible or as small as possible. Great question. Any others? Cool. All right, so that sort of concludes our discussion of barycentric coordinates, and it really is worth reviewing and understanding this concept because it's one that's going to come up over and over again. Because essentially, we're going to be rendering all kinds of stuff associated with triangles, and any time that we don't have that information in the interior of the triangle, this is kind of a reasonable standard way to interpolate information. And there's a lot of information you might want to interpolate. So for example, a different thing that we often do is attach a material model to every vertex of a triangle mesh, right? Like defines how shiny or reflective it is. And that might be spatially varying. It might be that like the material is scrubbed and gets less scrubbed as I move along the surface. Then a reasonable thing I might do is actually interpolate like the parameters of the material along the surface before doing that rendering calculation. Right, so there's a lot of different stuff that I might do. Okay, so that's that. So now we're going to have a bit of a grab bag of a few other kind of useful things to know about rendering, and the next time we're going to talk about how to accelerate all this stuff. For one, a really important concept when you're writing your ray tracing code is to write your code cleanly. That's important no matter what code you're writing, but it turns out in ray casting and ray tracing, that's particularly important and particularly easy in a sense. Because so far, we've already defined 3 different things that I could run array into, right? Like I could run array into a triangle, into a plane, or into a sphere. And for purposes of rendering, does it matter which of those objects my ray ran into? Well, in a sense, no, right? An object is just a thing that gives me an intersection point and a normal vector. And if I have those, I can do everything I need. So far. I mean, like there are obviously some like fancy materials where you might need other stuff, but for now, that's good enough. So hopefully many of us have encountered object-oriented programming before. I can never know at MIT. Okay, excellent. Well, if you think about it, like ray tracing is like the original object-oriented programming. Like it's actually objects, right? And in particular, one thing that we can do, and it's something you will do on your homework, is to define an object called object 3D. And essentially, that's just going to be a thing that defines a function intersect, right? Which is going to take the parameters of an array. And essentially, all it's going to do is say, yes or no, did that ray intersect this object? And if it did, return some information about the intersection point. What this is going to allow you to do is to make your ray tracer really extensible, right? Like, you can start by just working with spheres, and then later on, you can like extend your ray tracer by adding triangles, and it's just going to be like, you know, defining a new subclass of this object thing. And if your ray tracer is implemented correctly, you can just kind of plug that in and leave all the rest of your code the same, and it should work okay, yeah? And so essentially what you could do is, for example, make a plane, a sphere, a triangle mesh, like even like a group, which maybe just iterates over things in this interior, which are just all different types of objects. And essentially they're all treated symmetrically. In fact, in object-oriented programming, you tend to abstract just about everything in a ray tracer. I mean, you can do the same thing with like cameras and ray generation and so on. So essentially, these are great exercises for like good programming practice and that kind of stuff, which is nice. Similarly for materials, right? A material is really just a thing that takes like a normal vector, a light, and some parameters of your surface, and that outputs a color, right? Like I didn't actually need to know which material model it was. And so ray tracers are very clean things to implement. If you like this kind of stuff, there are like many famous books out there you can look at. The first one, you may recognize the last name of one of the authors on the first textbook. There are also lots of really nice ray tracing books, specifically like Pete Shirley's book was one of the first ones that I used to read back in the day. So now for the rest of lecture, we're going to start, and for the rest of like the next several lectures, we're going to be filling in all kinds of fun details to make our ray tracer handle more and more interesting objects and materials. And the first one we're going to do, we're going to start with, because it's really a cool feature of ray tracing specifically. It's something that's actually quite hard to pull off in other types of computer graphics. And that is the idea of constructive solid geometry, CSG. Wow, it's a groan and we haven't even started yet. All right, so what was that? This looks complicated. You look complicated. All right, so in constructive solid geometry, I'm going to do kind of arithmetic with shapes. That's our basic goal here. And it looks complicated, but it's not. And that's what's so cool about it in ray tracing. In particular, okay, we already know how to render triangles, so we can certainly like render a cube and a sphere. But what if I wanted to take like a spherical bite out of a cube, like the second thing here? Or I wanted to look at the intersection of a sphere and a cube, so like this little segment that we have on the right. Right, so all of these things are set operations, right? They're like set union, set difference, set intersection, all that kind of stuff. And this is also a common way to do shape modeling. In fact, if you have ever taken a computer-aided design course or like gone in the mechanical engineering department, I think this is one of the most common ways to engineer some pretty complex objects. Is to start with a few primitives. Remember that primitive is this kind of vague term referring to like simple shape we know how to implement. And once you start with primitives, you can start building up more complicated stuff by doing CSG. So that's what we'd like to do. And in fact, you can make some really nice looking objects using pretty simple stuff. So here's an example of like to me it looks kind of like a coffee table, maybe like a kid's toy, I don't know. Some weird shape. And essentially, I've shown you an entire tree worth of CSG operations that was used to obtain this. And it's basically really only constructed out of a sphere, a cube, and cylinders. Right, so here's how we did it. You can take 3 cylinders, which are axis aligned, and take their union, right? That's the symbol here. And that creates this little shape on the right-hand side. On the left-hand side, I could take the intersection of a sphere and a cube, right? And that gives me this like kind of capped object here. And if I take the left one minus the right one, so remember the set difference is all of the things in the left set that aren't in the right set, then what I get is the shape on the top. Does everybody understand how we're defining this shape? I haven't told you how to render it or how to model it yet, but just like what points would be inside and outside of this thing. Notice, by the way, we talked about object-oriented programming. This is another great example, right? Like there's this tree structure where all of the vertices are objects and somehow we're hooking them all together into this abstract thing. Here's another nice example of CSG. Here it's like a little shiny, whatever, lamp thing. Essentially, it's just constructed out of like some pretty simple building blocks. Okay, so here's our kind of simpler schematic of what's going on, right? I have a shape A and a shape B, and some of the basic operations that I might want to implement are like union, intersection, and subtraction. I would argue that rendering the union of 2 shapes is not terribly difficult. That one I think we could probably do by just rendering them both. But the other 2 are more complicated. Incidentally, even the union, actually, if you have like a transparent material, might be annoying to work with, right? Because like if I have 2 spheres that intersect, I might not want to see the intersection surfaces in the inside. So even the union is something you probably would want to implement. So, of course, there's a long list of binary operations, but essentially it just has to do with this Venn diagram of like points that are inside shape A, not inside shape B, or the other one. The question is, how could I render such an object? So like, let's say that I want the intersection of 2 shapes. So this feels hard. This feels really difficult, right? Like modeling that shape or describing like the intersection of 2 spheres is like a weird piece of geometry, right? Like modeling that thing would be a huge pain in the tuchus. Yeah, what do we think?
Like, couldn't you do the same thing we do ray tracing for like a sphere, but you just like do like if statements, like that, like you define functions for union, intersection, subtraction, and figure out like the distances?
Yeah, so that's sort of the right intuition. So here's, to summarize and put words in your colleague's mouth here, I think a good intuition is, or like a good question to ask is, do we really need an explicit representation of that shape? And the answer is no. Right? All we need to do is to be able to find the intersection between our ray and that shape. Right? That's our sort of clue. That's a great observation. So what can we do? Well, here's, oh yeah. Anybody?
Go ahead. Wait, so can we just find like, since you know like the intersection's gonna be a plane,
Mm-hmm.
can you just like, since you can calculate where like the ray's gonna intersect, can you just find that plane in terms of like, I don't think I'm saying right things.
That's okay. I feel like you guys are getting right. I want you to think critically. I feel like there's so many people that are not thinking carefully, just writing stuff down. Yeah.
Yeah, I would like go through the tree, and every time I try to find this point where my ray intersects the object, I
Mhm.
just look at if this point verifies the tree or is in that object but not in the other or something like that.
Okay, we're getting closer.
Condition that for every point I can verify using the tree if I should draw the.
The only problem is like you don't want to iterate over every point.
Oh, yeah, no.
Right? There's a lot of points in space. Yeah, but we're getting closer for sure. Yeah.
So I would think we would like do an intersection. So basically we find all the intersection points between our array and the object that we're interested in, and then kind of we want to see where like for example, if we want to render the intersection, we only want to render those points that would both intersect A and B. So we basically do our intersection,
Mm-hmm.
and then we check if we get the same point, kind of from both with intersecting with A and with B,
Mm-hmm.
and only then we draw it. But if we get different points, then we don't draw it.
Okay, so I think we're onto something, but let's see if we can refine it a little bit. Oh, we'll keep going. Yes.
You have to like look at the order of the intersections.
Yeah, that sounds like a great idea. In particular, is it enough to just know when an array enters an object? Nope. Yes.
No, there's like.
Thank you.
No, I'm saying something. You can keep track of like when it enters like a certain object and exits that same object, and the same for the other object. And then depending on what you're looking for, like the intersection or subtraction or whatever, you can decide on which entry or points to choose.
Yes, that is 100% right. That's perfect. Yeah, so smart. Yeah, you're absolutely right. So to kind of compile everybody's ideas together, I saw your hand too, and I forgot. Oh, MIT Ultimate? Nope. Okay. Yeah, that's absolutely right. So essentially, what we're going to do is interval arithmetic, right? We're going to extend our ray tracer in a tiny, tiny way, right? Our current ray tracer, objects just tell you when rays enter, right? Now we're going to make objects tell us the t when it enters and the t when it exits. Okay? And that's going to be enough information for us to do all of the CSG stuff. So to summarize a little bit, here's what we don't want to do is maybe like compute the actual like intersection of the two shapes, because those are probably pretty complicated. So instead, what we're going to do is just try to kind of figure out these intervals. And the good news is, like, for instance, if I were in A and B, then I just want to kind of intersect those things. And one-dimensional set theory is really not so hard, right? It's not so hard to take like two 1D sets and intersect them and so on. And so essentially, that's the really beautiful, cool thing about CSG and ray tracing. I never model this shape, right? I just do interval math, and then implicitly what comes out of my ray tracer is the right image. Right? This is so cool that this happens. Okay, so, right, so let's, sorry, my slide's a little out of order. So in particular, let's say that I have an object and it returns like an in function, which is the interval of t's where my ray is inside of that object, right? So between t equals 1 and t equals 3, I'm inside of object A. And between t equals 2 and t equals 6, I'm inside of object B. Yeah? Does everybody understand the notation here? Okay. So, ouch. Sorry. All right, so let's say, and now what am I going to do? Well, remember the nice thing about my object-oriented programming is I can make a new type of object, which is like the difference between two other objects, right? Backslash, by the way, means difference, right? Sometimes people use a minus. I like a backslash. Okay, so what is n of A minus B? Anybody? So first of all, what is A minus B in this picture? Is it, it's like kind of just this left, like it's like the circle chopped off, right? So what is n of A minus B here? So A goes from 1 to 3, B goes from 2 to 6. Yes? 1 to 2, thank you. Everybody see how we got that? Excellent. Let's do n of A union B. 1 to 6. All right, thanks, team. And finally, n of A intersection B. 2 to 3. I'm going to trust you. Okay. And indeed, we got it right. Go team. All right. So do you see how this is not such a hard extension of our ray tracer? We just return 2 things instead of 1. Or probably instead of 2, we'd return like a set, right? Because you could imagine a shape like the letter C, where you kind of enter, exit, and then enter, exit again. So you might want to be a little careful with that. And that's how you can render CSG objects. Essentially, what you do is make a new object, which is like the union or the difference of 2 other objects. And by extending your ray tracer just a little bit to keep track of intervals rather than just the first thing that you run into, essentially everything else works pretty easily. Any questions about that? Let's start in the back. Yes?
Is there a reason that you don't like go along T and assign different values? Like I guess you would say like the values in the set in A have like a value of 1, so you're going to render that fashion, and otherwise it's 0.
Mm-hmm.
Can you use that but with non like 0 or 1 values to render like transparency? Like,
Oh, yeah.
so like if you're going to an object, it becomes less clear. Or something.
Yeah, transparency makes this story a little more murky. Literally, I guess. I would say that you really have to, usually when you implement these kinds of things, you really want to separate out like the geometry and the physical object here. And so there's certain types of materials where the light intersects with the material and then continues to kind of interact with it as it moves through. So think like murky water or like marble. And then there are other ones where really the interesting calculation happens just when the light hits the surface. So if your volume were transparent, then you would have to decide, like for instance, if I take the intersection, does that mean like there's 2 times the density in that intersection region, or is it really just one object whose shape happens to be the union of these 2 sets of points? I think usually we think of that second case, in which case I think this is still valid and you'd use it for geometry and then you just have to do your shading in some other fashion. Where this gets complicated is when there's phenomena like scattering, where like the light doesn't just follow a straight path, and we're going to return to that a little bit later. It's a good topic for a course project if you want to, suffer. Yeah. Any questions? Ari? Yeah.
Yeah, so just to reiterate, when you're doing the subtraction, you're not actually subtracting the 2 shapes themselves. You're like subtracting these 2 points when that is the direction of the ray, like the ray's entrance and the ray's exit. Like the boundaries, like 1 and, for example, in A difference B, it's 1 and 2, that's the ray's entrance, the ray's exit, rather than the shape itself.
That's right. I never made a triangle, like a triangle mesh of that intersection. In fact, that's a hard problem. What's not so the point is that these are equivalent, right? Like, if I tell you this shape is the difference between these 2 things, I can intersect a ray with that different shape without ever actually representing that shape explicitly, right? And that's what's so like magical about this stuff, right? Like, on the other hand, let's say that I wanted to like 3D print A minus B, right? So in order to do 3D printing, I need to like actually fill a volume with this thing and have some representation of the surface. So if I wanted to mill it or something, then this would no longer be sufficient. I would like actually need a triangle mesh of this, and then you got to go take Piotr's class and like learn how to like mesh an object. that's a tough problem. Yeah.
Also, it'd be different for like CAD.
Yeah. So in CAD, oftentimes they have these kinds of representations, but CAD software isn't just a ray tracer. So they actually have an entire geometry engine inside of there that actually like work out like a triangle mesh of the intersection surface or something. So a phrase that you hear a lot in CAD is trimmed geometry, which would be like, I have like a square patch and now I kind of trim it with some other Bezier thing. And those get really annoying really fast. In fact, your TA Zoe just published a paper in exactly this space, and she can tell you that these are tough things to work with. Yeah. I saw a hand over here somewhere. Yes, over there, of course. Yeah.
So in this solid geometry, we're not representing these objects with any triangle mesh. We're just saying this is a square. Sorry, this is a cuboid or a cube. Right?
That's a good question. It could be a triangle mesh. I could have the bunny minus the sphere, and that would be fine. The only thing I need is that all of my objects need to be able to return that interval, right? And so I could easily take the intersection of a mesh and a primitive, two meshes, whatever. And the point here is that I can render it much more easily than I can represent it, which is kind of interesting, right? Oh, yeah.
So if I had like a small cube,
Uh-huh.
this is starting point. If I had a small cube,
Small cube.
then I could represent kind of any object or the world with just like the union of objects or the intersection of particular.
Yeah, I believe that's a Minecraft video game. Yeah. So you're right and you're wrong. So you're right. Like you can approximate about any volume with a bunch of cubes. I mean, calculus or Lebesgue theory tells you that too. Would you probably want to render it that way? Then I don't know, right? Because one thing that really matters for rendering is normal vectors, and of course cubes tend to be axis aligned. So like for instance, this thing, you just inherit the geometry of the two objects that you're messing with, right? So you don't somehow get more resolution than the input. Yeah. Yes. Yeah, so the question was how do we actually represent these things computationally, or like how do we store them? This is exactly why we have object-oriented programming, right? So we have this abstract class called object. If we want to do CSG, then your object is a thing that returns a set of intervals for like when array is inside of it, right? And I can make a bunch of different subclasses of that, right? I can make a sphere, which is that, and stores like a center point and a radius. I could make a union object, which actually stores two other objects inside of it, and then does a calculation that wraps around that, right? And all of those things are essentially just different instances of exactly the same abstraction. If it sounds scary, that's because it is to wrap your head around it the first time. But you'll see it's really not so bad, like when you implement. And in fact, there's a lot of cases where you'll do that. We'll see more of those later in lecture here. Yeah. Yes?
Trying to get practical and accurate design. So,
Mm.
so if I have these or an object that's defined as a tree,
Uh-huh.
I'm launching array at it. Now for every object in the tree, I know their interval, so I do all of these.
Do you ever actually have to write code that traverses the entire tree? No, a union object is just a thing that stores two other objects and takes their union, right? It just might be that one of those two objects inside the union object is itself another union object or an intersection, right? And so what happens is when I call that other object's ray intersection code, it might also recursively call somebody else's code, and I never have to know that in my implementation. That's the beauty of this abstraction. Mm-hmm. Oh yeah, you still have to implement interval arithmetic for sure. Yeah. Yeah. So I think a reasonable way to do that would be to sort, right? And yeah. Mm-hmm. Any other questions? I'm glad you guys are waking up. This is great. Yes. Mm-hmm. Yeah, so let's see if I can replicate your example here. So I want the intersection. So I have maybe, actually, I think a reasonable way to draw this would be like, well, no, okay. So I have some object here, which is an intersection, and you said there's a square here, and then this object is itself the union of like a square and a circle, like that, right? So this object is like a circly square, like that. Something like that. And then maybe I intersect it, so like I cap that, whatever it is. Yeah, so what's gonna happen here is like up here, I'm gonna ask like, what is the interval in which I'm inside of this object? this thing is going to ask its children, what interval am I inside of you, and what interval inside of you. And that's it. From this guy's perspective, that's all that matters, right? This child just so happens to store 2 other people that it's going to have to call that same function on, right? So it's going to compute that union down here, and then that's what's going to return up here. Similarly there, and then up here, you take another intersection of a set of intervals. Yeah. So the nice thing is that this abstraction, I never need to write code that explicitly like moves up and down a tree. I just talk to the things right underneath me. And like they could have all kinds of branching, and like that's totally abstract to me. It just doesn't matter. Yes? That's right. So like each one of these things is just returning a set of intervals, right? So so it would call to get the set of intervals from its children, and then do some processing and return a new set of intervals. Yeah. All right. One more question, then we do need to move on. Yeah. Ah, yeah. So that's a good question. So remember, in ray tracing, we don't just return where the ray intersects the object. We typically return some other information, like the material, right? And so probably what you would do is attach to the beginning and end of every interval some material information and kind of hand that up carefully. Yeah. Okay, so let's move on unless there's any like really burning questions in people's mind. Excellent. So we have our kind of grab bag of fun ray tracing topics today. Another thing that's just worth mentioning, there are a lot of boundary cases in ray tracing, right? There's a lot of like rays that might barely graze an object or something like that. Similarly, when we start doing like reflections, we're going to have to worry about like, I reflect a ray off of a surface, and I don't want that reflected ray just runs right back into the surface it just reflected off of. So the reality is that there's a lot of fudge factors in ray tracing code. There will be some global variable in your code somewhere called epsilon. And what you're going to have to do is just offset a lot of things. So for example, when I'm making that secondary shadow ray we mentioned last time, probably I point that ray toward the light, and I also maybe displace it along the direction of the ray just a tiny bit to move it off the surface. Another good example, which is really hard to get right, is like, well, which triangle did I intersect when I hit 2 that are sharing an edge? And again, the likelihood of these things happening is like 0 in real life, but the reality is that we often choose like integers for the coordinates of our camera or something. So these things just do happen in real life, and things we have to be careful with. So that's just a bit of a footnote. So for our last bit of class today, we're going to talk about one more of these nice abstractions in ray tracing, where I'm going to make an object that itself stores another object, right? Like notice that that's kind of what's going on here, right? Like I made an intersection object by like storing 2 other objects and messing with them. And that is applying transformations. Right? In particular, we know how to render a sphere, but what if we want to render an ellipse? Yeah, that's the real question we want to answer here. And of course, there's one way to do it. It would be like to store the major and minor axes of our ellipse and like do a bunch of ellipse ray intersection math. But we're going to try and come up with something clever where we're going to store a sphere and then like a transformation on top of it. Like I want to multiply its x coordinates by 2. And the question is like, how do I render that thing? Okay, and this is actually a broader example of a pattern called instancing, which happens a lot in rendering, where the reality is a lot of rendered scenes have a bunch of copies of the same thing, right? So like if I want to draw this, I don't know, checkerboard, chances are I don't need a 3D model of every single checker. It's just enough to store one and then just have a bunch of instances of this in my scene. Or similarly, if I have a bunch of stick figures doing some weird ritual here, then I probably only want to store one of those at a time, and that's good enough. Right? And so really the phrase instancing here is really just, you should think of it as like storing an object once and then using it many times. We've already talked about that. Right? We mentioned the scene graph data structure. Remember that one? Which is essentially some way of coping with this instancing idea. Okay, so in particular, so far we've kind of drawn just like canonical versions of objects, like a sphere centered at the origin. But I think a very typical thing to do would be to store like a transformation matrix that acts on the points of a domain. I just like lose half the class. So in particular, like maybe I store a sphere and then I also store a matrix saying I'd like to act on the x coordinate by scaling by 2 or something like that. Or like translation is probably a good one. Okay, so there are like 2 different ways to do this. And again, this is a great example where in ray tracing, I don't need a 3D model of every object in my scene. What I need is a thing that intersects my ray with that model. And that can mean a lot of different things for a lot of different objects. In particular, there's sort of two different ways that I could do this, right? One would be for every single type of object out there in the universe, I could just like force you in your implementation to deal with like scaling and translating and rotating that object. The other would be to just come up with a means of intersecting a ray with a rotated version of an object, for example, right? So in other words, I'm going to make a new object which stores an object inside of it plus a matrix, right? And says, I would like that matrix acting on this object stored inside of it. Does that make sense? So here's the trick. I can either transform the object, or I can leave the object alone and actually transform the ray. This is a sneaky trick. And so we're going to choose that second one because essentially making primitives that handle every possible transformation is going to get really annoying, right? So here's how we do it. Let's say that I have a matrix M, which is acting on our object, right? So for every point on our object, I apply M to it to get from object space to world space. Then if I apply M inverse, I'm going from world space to object space, right? And here's a really nice thing. If I have a linear transformation of space, I mean, the word linear should kind of give it away. When I act on a ray, it stays a ray, right? Like it doesn't like turn into a semicircle or something crazy. Yeah? And so what does that mean? That means that I can either transform my object or I can apply the inverse transformation to my ray. Okay? So here's the trick. If I have a ray, remember that a ray is specified by two things, an origin and a direction. What should I do? Well, if M is acting on my object to bring it into world space, then I can instead apply M inverse to the origin and the direction. Remember back to like lecture 2 or 3 here, we'd have to be careful with our fourth coordinate and projective space for that one. Right? One of these is a point and one of them is a vector. And now I get the sort of the ray from the perspective of the object before the transformation was applied to it. Does that make sense? So I can either stretch out and translate my ellipse, or I can leave the ellipse as a sphere and instead kind of translate and stretch out the ray that corresponds to this thing. Okay, so what do I do? Well, I now intersect this ray with this thing in object space. And what is the t in the original space for the intersection? It's actually the same. I just can reuse the same value of t. So again, rather than transforming my object, I'm going to transform my ray. And notice that this is another great example where I can like store an object in the inside. When I want to ray trace a ray intersected with my transformed object, well, my kind of wrapper thing is going to just mess with the ray and then call the object's ray intersection code with my kind of transformed ray instead and use that to compute the intersection. I feel like those words sounded like a lot, but it's actually not terribly complicated. We're just messing with the ray and then intersecting again. Okay? There are a few details you have to be careful about. Often by convention, we store the direction of the ray as a unit vector, but like, for example, let's say that my transformation just like doubled the size of something, right? So then the direction of my ray would actually half, right? Because it's M inverse. That's perfectly fine, right? Like I didn't say that like rays have to have unit length for direction, but sometimes your code might assume that by accident, and that's a common source of bugs. The most common solution here would be to just write code that can deal with non-unit vectors for the direction of a ray, and that's perfectly fine. Yep. So the slides go through this, but really you should just use solution number 2 and make your code right from the beginning. So when I render, again, remember what do I have to do? An object reports an intersection point, and it also returns a little bit of information about the intersection point, probably the normal to the surface. Right? So I can get the intersection point easily enough, right? By transforming my ray, finding that t, and now just plugging that t back into the untransformed ray. Now I get the location of the intersection. I also need the normal to the surface at the intersection point. What should I do? You guys, I think you have to implement this on your homework due tomorrow, yeah? Right? If I have a normal vector to a surface and I apply a transformation to it, what happens to the normal? I have to apply a transformation to the normal. Of course, that's what I heard. What transformation should that be? The inverse transpose. That's right. Yeah. So this is just to remember, if I have my transform object here, right? So remember, that means that I have a matrix, and then I've got like another object stored inside of it that I want to intersect with. Then what I'm going to do is transform my ray, find the intersection point and the normal in that transform space, and then I got to undo it all, right? I got to go back to my original coordinates. So to do that, right, I'm going to apply my matrix to the point and the inverse transpose to the normal to get the normal in the world space. Does that sound familiar? Remember that normals transform like inverse transpose. If we forgot that, that's okay. We just go back to the old lecture and review. Okay, so that's the basic summary here. Is like I've now given you yet another object that you can define in your ray tracer, where your object is really a transform applied to another object. And the way that I'm going to intersect my ray with that thing is by transforming the ray instead of the object, intersection, and then undoing all of that. Okay? So notice that we now have two different examples where I didn't actually make an explicit version of my geometry. Right? Like for instance, if I wanted like a bunny that was scaled by 2, I didn't like loop over all the vertices, multiply them all by 2, and then render it. But I was still able to intersect a ray with this thing by using the right abstraction. So that's what makes ray tracing really, really powerful, is by adding these just like small modules to your code, you can just make it more and more complex, and somehow the code still remains pretty clean. The problem here is that it's a little too easy to add complexity, right? Like you can make like complicated unions and intersections. It's also not so hard to render fractals using this kind of thing. You could like add fancy materials and lighting and shading. And pretty soon, you're going to be traversing a really complicated tree worth of computation. What do you think is going to happen to the efficiency of your ray tracer? It's going to go to 0. It's going to be really, really slow. And moreover, you're going to be traversing all kinds of tree kind of data structures. So parallelizing your code is going to be kind of tough. And so in our next couple lectures, we're going to talk about how to make your ray tracer fast. When I say fast, I mean fast for a ray tracer. Which is different from fast for rendering altogether. I think there are very few ray trace video games. Anyway, everybody seems ready to go, so we'll call it for the day. If you haven't done your homework yet, I would suggest you try that, and we'll see you next time. All right, let me